In this video, we're going to take a look at polynomial functions and some properties, specifically the end behavior of their graphs and zeros or x-intercepts of their graphs as well. So in our list of topics for this video, to do these things, we need to understand the degrees of terms and of the polynomial itself. What's the lead coefficient and what does it tell us? End behavior, and then how the degree of the polynomial function gives us information about how many zeros or how many x-intercepts there are. So we're going to go ahead and start off with this cubic function here. Terms are separated by the plus sign, and they keep their signs. So I'm circling each of the terms of this polynomial function, this cubic. So my terms are x cubed, 6x squared, 11x, and 6. The degree of the polynomial terms is the power on the x. Another way to think of that is how many x's are being multiplied. So x cubed tells me that there are 3 x's being multiplied, and that's the information that the degree gives us. So as we go through and identify the degrees of each of these terms, I've got degree 3, degree 2. In 11x, there is a single x being multiplied, and in just 6, there are 0 x's being multiplied. We can think of any constant as having an x to the 0 attached to it. Not really helpful, but it is for the degree. 6x to the 0 is really just 6 times 1, because x to the 0 is 1. Okay, so just a little background there as to why we call that 0. So the number of x's being multiplied. The coefficient is the numerical multiplier in front of each term. So if I start here with the second term, we can see that there's a 6 multiplied in front of x squared. So that coefficient is 6. For the first one, the x cubed, I could think of that as a single x cubed, or 1 times. So my coefficient there is 1, 11, and then for the constant term, it's just the term itself, 6. Okay, what is the lead term? The lead term is the one with the highest degree. Let me go back to my purple pen here. So this would be the highest degree term. Regardless of the order, in this case, my lead term does show up in front, and it's x cubed. The lead coefficient then is 1, and the overall degree of the polynomial, it's also that highest degree, and it's the degree of that term, 3. So this 3 gives me the degree of the polynomial. Okay, next we want to graph and state the zeros. So let's go ahead and get this into Desmos. So I'm going to open up Desmos here. You can tell I use it a lot. It just shows right up in my browser. And I'm just going to pull this apart as its own screen so we can get both the worksheet and, let me close this guy. There we go. So we've got the worksheet and Desmos together on the screen here. We're going to look at quite a few graphs. Graphs are a great way to check out the behavior of any function. Okay. So let's go ahead and put this function in. You could do y equals, or you could do an f of x equals. It doesn't matter. I'll do f of x equals x, and then the caret is shift 6 cubed, arrow over, and then I want plus 6x squared, again, caret on the 6 for the 2, and then plus 11x plus 6. Okay, let me make this large so we can look at the zeros of this function. Desmos does such a great job because it puts, I'm just going to zoom in here a little bit. It puts a dot, whoops, let's grab that. It gives you these as points that you can click on. So I just clicked on the graph again to bring those points up. And I can go ahead and click on it again to go ahead and hold those. It knows that these are important points. So it's giving me the value at each of the zeros. A 0 is an x-intercept. So we've got our x-intercepts here crossing the x-axis at -3, -2, and -1. It also gives me the values of these turning points. These are also important, these max and mins. So it's approximated the values of those turning points, which is great because before we get to calculus, where we do something which is taking a derivative, the slope anywhere along a curve, it's really difficult to find the exact value of a lot of these turning points. But what we really want here are the x-intercepts. And we can see really nicely that we've got those at -3, -2, and -1. Let's go ahead and put that onto our worksheet. So -3, -2, and -1. And those zeros are just the x-intercepts. A really good way to think about why they're called zeros is because their value, when you put any of these into the function, it gives me a zero back. So if I were to put -3 into my function, actually, let's do this with Desmos because it's going to make our job a little bit easier. There's Desmos. So if I were to go down here to an empty cell and ask my program to evaluate the function at -3, so what's f of -3? Sure enough, it says 0. And I can confirm that each of the values, as I plug that in for x, give me a 0. So a couple different ways of thinking through that language. Okay, let's take a look at the next example. So in our next example, we've got two terms, but again, those terms are separated by their signs, and the signs stay with the term. So my terms are 18 and -2x squared. The degree is the number of x's being multiplied. Well, there are none in 18. And for 2x squared, there are 2. That's the power on the x. The coefficient for the constant term, it's just the number. And it's going to be the number multiplied out in front for the -2x squared. For this one, it was not given to us in descending order. The 2x squared showed up second, but we still take the highest term, the highest degree, to designate that lead term. So the lead term is -2x squared. The lead coefficient then is -2, and the degree is 2. I'm just getting both of those from the lead term. -2 is its coefficient, 2 is its degree. Now I want to graph and state its zeros. This is a quadratic. This is a degree 2. So it is a transformation of, and we can think of this as a transformation. It's a transformation of x squared. And as I'm looking through the transformation, I've got only transformations outside of the function, outside of the x squared. So I've shifted it up by 18. I have a stretch here of 2 and a reflection, which is my negative. So I can actually sketch it here, but I'm going to go ahead and put it in Desmos as well. So it's going to be up here at 18. It's taller and reflected. So I get a lot of really nice information just from the lead term. The lead term had a negative, so it told me that it opened down, and it had a 2 on it, which meant that it was a taller looking parabola. Let's just confirm this with Desmos. And I'm going to just get rid of what we had here. And this one is f of x equals 18 minus 2x squared. Okay, let me make this large so you can see. I know I need to go up to 18 there to be able to see it. So I am just zooming to be able to see that. The other way that you can do this is remember with your wrench for the graph settings. I know that it's going to cross at 18 on the y-axis. So it actually did a good job here. So maybe I do want to see from -5 to 19 or 20. So you can just change these. And then on the x-axis, you can play around a little bit with these. Maybe you want to go from -7 to 7 or something like that. Knowing from the transformations what you're expecting really helps kind of zero in on what your function is going to look like. Okay, so here it is. It's crossing, it looks like at a -3. If I click on that, Desmos will confirm that. Yep, -3. Notice how it matches that to a 0. and 3. Again, we can easily confirm that these are zeros of our function by just evaluating. F of 3 is in fact a 0. And if I put a negative in front of that, same thing. That one is also 0. So that gives me my x-intercepts. Let's go back to the worksheet. And we've got the zeros now that we can go ahead and fill in. It crossed the x-axis at a -3 and a 3. So my zeros are -3 and 3. Okay, next, end behavior. Well, this gives us some really good information about behavior. Notice with that quadratic, actually, that's a good one to take a look at. So with that quadratic, I was able to tell what my function was doing on either end because of that lead coefficient. I knew that instead of opening up like x squared would do, the negative in front of that turns it. I've got that vertical reflection and it opens down. So the lead term becomes really important because it gives me the direction, whether it's opening up or down, and the degree. The degree gave me the shape. So because it was a quadratic, I knew that it was a parabola. Okay, so that's where we're going to get our end behavior. So on my graph here, I've got my x-axis, and I have positives on the right and negatives on the left. So over here, x is going to really, really large positive numbers. So we'll say that it's heading to infinity. Over here on the left, x is going to very, very large negative numbers. So we'll say that it's heading to negative infinity. This gives us our domain behavior. I can also talk about function behavior. Let me grab a different color pen by using the f of x axis or the y-axis. So that's going to be my vertical axis. If I'm heading up on the y-axis, I'm heading to really large positive numbers. So I'm heading to infinity. And if I'm heading towards the bottom on my f of x or y axis, I'm heading towards really big negative numbers. So this is heading towards negative infinity. So I'm going to be using this diagram as I'm doing end behavior for different graphs. Let's go ahead and take a look at, instead of doing a transformed quadratic, let's go ahead and just take a look at a quadratic. I don't even need here to graph it. I know what this guy looks like. It looks like this. So I'm going to start by looking at the left side of the graph. So as I'm looking at the left side of the graph, let me see if it will let me highlight it here. I'm looking at this piece of my graph right here. What is my function doing on the left? As I'm doing my behavior, in order to talk about the left side is when x is moving towards infinity. I actually want that green. So picky with my colors. Okay, so I want that to be green. So on the left, x is heading towards infinity. That's what left means. Negative infinity, I should say. And I want to take a look and see, what is my function doing? Well, my function is going up towards the positive direction. So I can say that my function, f of x, is heading towards positive numbers, is heading towards infinity. So on the left, as I'm going to do this all in one color. There we go. So to say left, we say x heads to negative infinity. F of x heads towards these positive numbers. It heads towards infinity. Let's go ahead and do the same thing on the right. So I'm going to highlight the right-hand side. Let's highlight it. I'll just do yellow again. Okay, so if I highlight the right-hand side, here it is. So I'm on the right. To say right, using my notation, I need to go ahead and go on the right side of the graph, which is x heading to infinity. So to say right, x is heading to infinity. I'm going to look to see on the right-hand side, what is my function doing? It's heading up towards positive infinity. So f of x is heading also again towards positive infinity. This is my right-hand behavior. Let's go ahead and just put this into our little box here. And I'm just going to add a little bit of wording here because I think it sounds nicer. As x goes to infinity, this means on the right side of the graph, what's my function doing? It's going up. So f of x is going up to infinity. I'm going to do one more thing on this diagram. It's really helpful just to have some normal words instead of all these symbols. So f of x going to infinity means up. F of x going to negative infinity means down. X heading to negative infinity is left. X heading to infinity is right. Okay. A little bit of a learning curve with this language, but this diagram is really going to help. Let's go ahead and take a look at x to the fourth. So I know that I've got a degree. So this one's degree 4. And I do not have a negative out in front, so there's no reflection. Let's go ahead and put this one into Desmos. We know what the quadratic looks like. What does the, I'm just going to type over this. What does the quartic degree 4 look like? So x to the fourth. It looks a lot like a quadratic, right? It's a little bit flattened in the middle. Do you see that kind of flattening there? So it's a little bit flattened in the middle. And if I go ahead and put x squared next to it equals x squared in a different color. There we go. X squared is in black. You can also tell that x to the fourth is taller. That makes sense, right? I'm taking numbers to the fourth power. Like 2 to the fourth is going to be bigger than 2 squared. So it's flatter in the very middle, but taller on either end. Otherwise, it kind of looked the same, right? Other than the way that it's stretched a little bit. But you'll notice that it has the same exact end behavior. So if I go to my worksheet, I'm just going to sketch this guy. It's going to read a lot the same. So am I in purple? Yep. Okay, so let's go ahead and just graph this guy. Okay, it's taller, but flatter in the middle. That's not a great graph, but good enough for end behavior, right? So I can see whether I'm working on the left or the right. So left or the right. I take a look to see what my function is doing. On both sides, my function is going up. Let's go ahead and put this into symbols. So on the left, my function is going up. So I want these two. And on the right, x goes to infinity. My function is going up. So I put those two together. Okay, so here comes my language. So as, this is how I say left, x goes to negative infinity. That's on the left side of our graph. What's my function doing? It's going up. So f of x goes to infinity. Now let's move over to the right-hand side. On the right-hand side, to say right, as x goes to infinity, that means right. My function is going up again. So f of x goes to positive infinity. Yeah, perfect. Now I'm using f of x here. You could use y if you wanted, or whatever the name of the function was. Just nice to keep it simple with f of x. Okay, number 3. So number 3, the only difference between number 2 and number 3 is this negative out in front. So that means we have a reflection. I do not need Desmos to graph this guy. I know that it's just going to be turned upside down. Okay, so it's going to be turned upside down. Just need a little bit of a sketch. So I'm going to label this guy first. So left, right. My function on the left is going down, and on the right, it's going down. Let's go ahead and express that in terms of end behavior. So on the left, to say left, as x goes to negative infinity, the function goes down, f of x, down, also known as negative infinity. On the right, to say right, as x goes to infinity means right, my function goes down, f of x goes to negative infinity. So just knowing the degree and whether or not we have a negative in front tells me the end behavior. Let's take a look at some odd degree power functions. X cubed is a really familiar one to us. It's one of our toolkit or common functions. It looks like this. If I do a little bit of labeling with my green pen on this guy, on the left, it's going down. On the right, it's going up. Let's go ahead and express that one using our end behavior. So as left, x goes to negative infinity, my function goes down, f of x goes to down is negative infinity. On the right, to say right, as x goes to infinity, my function goes up, f of x goes to infinity. X to the fifth. X to the fifth. Let me put this in Desmos really quick. Probably have a guess. It's going to be flatter in the middle, taller on the sides, if that was your guess. If it wasn't, it should have been, right? So let's go ahead and put in x to the fifth. Okay, there it is in green. And let me change my other one here to just cubed. Okay, so you can see how my green function is, there you go, flatter in the middle and taller on the ends. But it doesn't really matter in terms of end behavior. It's doing exactly the same thing. So just knowing the degree and whether or not you have a negative is all you need here. So the end behavior is completely determined by this lead term, x to the fifth. Okay, so I'll kind of do a goodish job there. Goodish is really all I need because I just need to be able to say that on the left, I'm heading down, and on the right, whoops, right, on the right, I am going up. Okay, so in behavior, as, let's see, on the left is x going to negative infinity, my function goes down, f of x goes to negative infinity. Same exact end behavior that we had before. As x goes to infinity, that's how we say right, the function goes up. So these odd degree functions have opposite behavior. Now we're going to put a reflection in there. Again, I don't need Desmos. I know it's just going to do this. Turn it upside down, flip it vertically. So I'm going to label one more time. Left, up. Right, down. Putting that into symbols. As x goes to negative infinity, f of x goes up infinity. On the right, as x goes to infinity, f of x goes down, so f of x goes to negative infinity. So to kind of summarize, if you have an odd degree power function, it doesn't matter how many terms you have, it's the lead term that we're going to be looking at. The end behavior is opposite. One up, one down. For even degree, for the even degree ones, the end behavior is the same. Either both up or both down. Okay, so we're kind of getting the hang of it. Now we're given these kind of ugly-ish functions, right? They're the ones that we had from up above. But I don't care what's happening to the entire graph. I really only care about the end behavior. I am going to go ahead and graph this first one, but I really don't need to graph any of these. I only care about x cubed. So I'm going to show you, if I can remember what I think I can remember. Let's get rid of these guys. And let's bring this back to the center there. Okay, so f of x equals x cubed plus 6x squared. I'm just guessing, and then I'll go back and check. 11x plus 6. Let's check. Probably not. Oh, I'm amazing. Okay, x cubed, 6x squared, 11x plus 6. Awesome. So let's go back here. I don't care. I'm just looking at end behavior. So it doesn't matter what's happening in the graph. It has a couple of turns, but it doesn't matter. We saw this before. I see the opposite end behavior. It is going down on the left and up on the right, just like any cubic. So on my worksheet, I know that it's going to be like I mean, a lot's gonna happen, right? But it's gonna look kind of like a cubic. So if I take a look at my end behavior, other stuff's gonna be happening, but on the left, we're going down, and on the right, we're going up. So for my end behavior, I can say, let's do the left first. As x goes to negative infinity, that's a negative, f of x goes down, negative infinity. And then for my right end behavior, as x goes to infinity, it always starts the same way, right? F of x is the only behavior that's going to change here. F of x goes up, which is infinity. Okay, part B. I don't care about the rest of this function. I only care about the negative and the x squared. So I know that whatever this function happens to be doing, it's going to look like a reflected parabola on the ends. So we can go ahead and quickly label our end behavior here with words. So on the left, it's down, and on the right, it's down. So putting that into symbols, on the left, these always start the same. As x goes to negative infinity, what's f of x doing? It's going down, negative infinity. On the right, as x goes to infinity, f of x also goes down, goes to negative infinity. So all based on the lead terms. I don't need to look at, oh, it doesn't like it when I'm using a function. There we go. All based on the lead terms. None of the other terms matter, just those lead terms. But it's so quick to graph them as well. So finally, we're going to take a look at some zeros of polynomial functions, and we're going to do this in the context of the fundamental theorem of algebra. That's a really weighty name for this theorem, fundamental, like it's the most important thing. I don't think it is the most important thing, but it's actually a really nice visual theorem or statement about polynomial functions. So for a polynomial function of degree n. So for a polynomial function of degree n, we actually have two results here. So number one, there are at most n real zeros, also known as x-intercepts. Number two, there are let's see, we can say there are at most also. So at most, n minus 1 turning points. A technical word for turning points is a relative extremum. Relative extremum. Okay, so that just means a turning point, so a max or a min. Okay, so n minus 1. So super visual, we can graph these, but really for the number of real zeros, I just need to know the degree of my polynomial function. So I just want to reiterate here that these polynomial functions consist of terms. There's no square root with an x inside of it. There's no fraction with an x in the denominator. So these are polynomials term by term. And there are also no negative exponents. So just to make sure we know what we're talking about with the polynomial functions. So for the real zeros and for the turning points, I just need to look at the lead term. I don't care about anything else. So the maximum number of real zeros is 3. For part B, the maximum number of real zeros is 4. I'm going to go ahead and pick on 3x to the 4th plus 2. This one has some really nice transformations in it, which is why I chose it. I know that I'm going to get that x to the 4th graph stretched by a factor of 3, shifted up 2. So it's going to be pretty steep, kind of flat in the middle, right? I don't do a good job of that, but it's going to look like this. Notice how this guy never crosses the x-axis. So when we say maximum number of real zeros, we really do mean maximum number of real zeros. I actually don't have any real zeros in this case, so there are none. But I know how many I'm expecting, as opposed to this last one, which, do I still have this guy graphed? I do. So as opposed to this last one, this was degree 3, it does have all 3 of the real zeros. So I've got 1, 2, 3 of my real zeros. So, and I've got my 2 turning points. So there's that n minus 1 turning points. So the maximum number, you just know how much you're expecting. This is really helpful when we're doing the math to try and find what the values of those zeros are. Okay, so what is the least degree of the functions graphed below? This is based on turning points now. So I'm not basing this one, the zeros aren't really helpful here. This one has 1, 2, 3 turning points. So I know that this guy's got to be, if I do my +1 business here, so this one has to be at least degree 4. So I know that I'm going to have those turning points. So it could be a higher degree. Notice the end behavior. It definitely has to be even. So it could be actually degree 6 or degree 8, but a minimum degree here would be degree 4. Okay, take a look at this guy. This one has opposite end behavior. So I know that this guy's got to be odd in degree. But take a look at the turning points. There's one there, tiny one there, tiny one there, tiny one there. So I've got 1, 2, 3, 4 turning points. 4 turning points, I do my +1, and this is at least degree 5. It could be, so degree 5 or 7 or 9, right? Dot, dot, dot. But there's no way that this guy could be an even function.